A very good morning, good afternoon and good evening to all my dear friends, participants and students. A very warm welcome to this course under NPTEL MOOC, the title of which is Application of Forecasting, Regression and Time Series Models. My good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, the three main topics which are planned and will be covered under this course are: the first one is forecasting, second one is regression, third one is time series, and we are in the midst and the middle of regression models and their concepts. This is week number 8, lecture number 38. Now, what is the coverage in this lecture? We will consider examples of MLR in other areas. We have considered in finance, and we have also tackled the problem of MLR considering the bird problem, swallows breathing in oxygen and breathing out carbon dioxide. So, that data set was 120. In the last class, we started about trying to understand the pollution level in a Scandinavian country, and I mentioned that as we were short of time in the last lecture, we will again a fresh start with the data. Just briefly, we have already explained and then move forward with the analysis of the problem. Data is 500 in number in the Norway, and the data time frame is from October 2001 to 2003. The data points in the first column is related to y, which is the dependent variable, and the later set of columns which are from column 2 to 7 are the 7 number of independent variables, and they had been explained and mentioned in the last lecture. The link you can find out and the detailed description of the data set is already given here in this slide, which was also discussed in the last class. Because you can click it, once you have the slides, you can definitely click it and have a look at that. Now, once we have that MLR model in the theoretical sense formulated with considering beta naught is there, which is the intercept, the actual model is this, where which I will highlight using a different color, which is red. So, you have y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus beta 6 x6 plus beta 7 x7, because there are 7 independent variables plus the error term. Now, what are the different variables which are there? It is written here, and I will come back to that once again. Y is NO2 concentration, nitrogen dioxide concentration, x1 number of cars per hour, x2 temperature 2 meters above ground in centigrade, wind speed in meters per second, x4 is temperature difference between 25 meters and 2 meters from the ground in centigrade, x5 wind direction 0 to 360, x6 hour of the day, and x7 the day number. Now, if you remember, I did mention that we will take the logarithmic of this concentration, and this concept why we are tempted on many of the problems we take the logarithmic of the value of either x and y is for the fact because it is one of the easiest transformation to do in order to check the random variable whether y or x is normally distributed, because normal distribution corresponding to the fact for x1 to xk and y is one of the important assumptions for MLR model. And apart from that, the linearity concept, the concept of independence between x1 to xk as well as with respect to the errors and vice versa, and also the concept of these ideas of homoscedasticity, heteroscedasticity, which holds, which does not hold, autocorrelation, non-autocorrelation, all these things are also important. An error term is with 0 mean and with a fixed standard deviation. Standard deviation on the variance of the error does not change with time. When I find out the correlation coefficient for the sample, correlation coefficient is rho hat I am utilizing for the estimate. The correlation coefficient, the principal diagonal obviously would be 1 as shown here, and the of the diagonal element are equal. So, if I basically concentrate, the correlation coefficient between x1 and x2 is given as plus 0.07. If I consider the correlation between x6 and x7, I will use a different color, is given as plus 0.2780. If I consider the correlation coefficient between the x1 and x7, it is given by plus 0.01040. If I consider the correlation coefficient between x3 and x7, it is given as minus 0.10630, which means the positive and negative correlation for all the random variables which are x is given. Now, immediately many of you may ask that we consider the correlation coefficient existing between the x should be 0 because they are independent. Absolutely right. But what we wanted to make you understand that in many of the practical examples, it may not be possible. Theoretically, you can build up a MLR data set for which all the assumptions which I have been repeating from day one when we started the MLR model or the regression model part for this course, the assumptions which are 5 in number I had been mentioning. That does not hold in the practical sense, but if you look at this correlation coefficient, those values are almost all of them are in the tune of 10 to the power minus 2. Like if I take this value, while I will put a tick mark in red, this value comes out to be about 1.250 into 10 to the power minus 2 with a minus sign, which is negative correlation. If I consider the other value, I am putting a double tick mark, it comes out to be about 2.42 in 10 to the power minus 3. So, these values are quite small or quite low. So, in many of the practical sense, you can consider the concept of independence between the x1 to xk, which here in this case k is 7, holds true. Practically, we can go ahead and solve the problem. Theoretically, the assumption of normality, assumptions of independence between x1 and x2 obviously is always important. Normality distribution and all these things can be plotted for this 500 set of diagrams for data points considering from x1 to x7. I have not done that, I will immediately go to the direct problem. When I solve the problem, now here I am skipping few concepts which is not that it's important, but not that important for this course considering the coverage we have planned. So, the MLR finally used is of this form, where we consider that initially we consider beta naught, then we consider from beta 1 to beta 7 considering x1 to x7 are considered as the independent variables. But after finding out the best fit model which will perform and give us the best multiple linear regression model, we find this is the MLR model we are going to take, where there are only 3 number of independent variables which is or which are x2, x3, x6. What is x2, x3, x6? They are temperature 2 meters above the ground in centigrade, x3 is the wind speed and x6 is the hour of the day. Once we fit that model, solve the model using the same concept, like we find out beta hat, we know that when you find out covariance of beta hat, then we need to find out S square, all these things. One beta hat is found out, the beta hat values, because there are k, here beta hat is 4, k is 4, because you have beta naught, beta 1, beta 2, beta 3. Beta 1 is beta 2, because depending on x2 random variable. Then the next beta value is corresponding to wind speed, and the last beta value is corresponding to hour of the day. And once we have that, the regression model gives us the answer, where beta naught hat is given by plus 5, I will only read till 2 places of decimal, plus 5.13, beta 2 hat is minus 0.03, beta 3 hat is minus 0.20 and beta 6 hat is minus 0.05. So, regression coefficients are given for this model and we can plot the model. Now, when we do the ANOVA plot is basically the analysis of variance. Main idea I am going to come to that. I have the degrees of freedom. So, based on the value that is 500, 500 minus 1 is 499, that is the total we get. Residual errors is given for, because you are considering these values of n minus k, k is 4, 500 minus 4 comes out to 496, and 4 why? Because you are considering the concept of beta naught also is in the model. Technically, it is n minus k and that minus 1 is coming from the fact is n minus 1. In the initial model, if you consider that we are taking, when we take the r square adjusted, in the 1 minus that SSE divided by n minus k, n in the numerator and SST divided by n minus 1 in the denominator, that will give you the r square adjusted value. So, once we have this, the values of sum of squares are given for the regression part, for the error part which cannot be explained, it is outside, that is given, and when you find out the total SST, that comes out to be the third one where I am putting a triple tick mark. So, again if you see it, I am reading without the decimal, the SSR value is about 157, the SSE value is 564, which is definitely high, and total value comes out to be 721. So, obviously, it gives you an idea that the r square and adjusted r square values will be low. Then when we find out the values of mean squared, the values are given. Mean squared are basically divided by the number of the values of degrees of freedom. So, 157 divided by 3 comes out to be approximately 52. Then 564 divided by 496 comes out to be approximately 1.13, and based on that you calculate. So, once I find out r square using this formula, the value is 0.22, 2 places of decimal. When I find out r square adjusted, it is given, every formula is given in this slide. When you have a look at the slide, you can understand. Here n minus 1 is 497 and the corresponding values of n minus this value of n minus k and the value of n minus 1 is 499. So, when you put this value, again this comes out to be 0.22. Now, there are 2 sets of information I want to pass on. The model is definitely whatever we have done, and based on the best choice model, it is not giving a very high value of r square. That is number 1. Number 2, when we do the adjusted r square value, obviously it is not increasing. So, the question may arise from all the participants and the candidates that cannot there be a better model? Answer, yes, they can be. And the second question is that the adjusted r square value is not increasing. Yes, it is not increasing. So, obviously, it depends on the actual model we have considered. Based on finding it out, the r square value and the adjusted r square value, if the value is changing on the positive sense, that means adjusted r square is increasing, then obviously it is going to make sense. Here it is more often hands-on training, hands-on explanation that what is the significance of r square, what is the significance of adjusted r square, what is the significance of beta hat, what is the significance of covariance, what is the significance of s square. So, through different models in different areas, that idea is being told to all the candidates, all the students time and again, because we have solved the problems based on finance, solved the problem in the area of ornithology for the birds, solved the problem in the area of pollution control which we are doing, and further on we will solve another problem in another stark different area. So, all these 4 to 5 different area problems would definitely give you a much good background in trying to understand the implication of MLR and how they are used and what are the results and how you analyze it. The 28th problem is totally in a different area. This is the secondary source data obtained from one journal, Statistics and Probability Letters, and the data can be found out. This came out in 1997. All the information about the journal, the writer, what is the title of the paper, the year, page number, volume, everything is given. So, if you check here, you will find it out. And what it contains is very interesting. It contains the information on the variables used using all the block groups in California, and that is being utilized to find out the following. In this sample, a block group on an average includes 1425.5 individuals in an area, particular area, living in a geographical compact area in the in the state of California in US. Naturally, the geographical area included varies inversely with the population density. Higher the population is, and obviously in the inverse direction, the geographical area is included. And in totality, there is quite a big data number, is 20,640 observations on 9 variables. And what we want to do, we will come to that. The authors of this paper have computed the median distance between the centroids or the centroids of each block. So, if you consider block, the distance between the centroid of the blocks are considered as latitude, longitude to give the information. They have excluded all block groups reporting 0 entities. The data file considers all the variables, and the information can be found out at this link. The link is given. So, it contains what are the information? Median household value, and that is important. Based on some information, the authors want to find out what is the median house value or the price, and that they are considering depends on median income of the family, the median age of the house, what is the total number of rooms, what is the total bedroom, what is the population, what is the household numbers, the latitude, longitude in all that particular order. All the information is given in this URL. So, the information about what is x and what is y is given, where I will mark the x and y in different colors. I will use a different color for y. So, main thing to find out is the median household value. This is important, and based on these set of data or the variables, which is marked in green. So, once you have that, then you formulate the MLR. Now, let us pause, and why I am pausing, this is important. Further details can be found in the journal and the article and the link, and we are omitting it, but I am just highlighting the point. The authors use multiple linear regression technique to find out the regression model and predict the price, and here it is important. Rather than the price, the actual median household value, they are taking the ln of that, because when they plotted the ln of the median household values, that came out to be nearer to normal than the median household value. Hence, the concept of transformation which I was talking about in the last 2 lectures is important. So, rather than taking MHV, the logarithmic values are taken. That is number 1. Number 2 point is, I will mark few variables, and that is important for your understanding. So, I will mark them in violet. So, beta naught, where it is important, I will mark. Beta naught is the intercept, beta 1 into median income is the first variable, median income is the first variable. So, I will mark with it as x1. The second one, which is important, and I mark with the different color for a reason. So, rather than take MI, which is the median income, the square of that is taken and tested, that is near to normal. So, that would be x2, in the sense MI square is x2, not MI. So, here the important concept would immediately, it should ring a bell, that the concept of linearity is based on the fact for the beta values, because rather than having beta 1 square, beta 2 square, which is not needed, because linearity of the model is based on the fact for the concept of the coefficients. X1, x2 need not be linear, they can be square, cube, 3 to the power 3/4, depending on how close that random variable is to normality. The third random variable is x3, which is mi cube. The fourth random variable is given by ln of median, I think, let me go back, it is MA, median age. So, median age is given, then you have the total room by population is given as x5, ln of that is also normal. Then bedroom by population is given as x6 and ln of population by household is given by x7, and the last one is household ln of h is given as x8. So, technically you have x1, x2, x3, x4, x5, x6, x7, x8 and the corresponding random variables are as follows. Again I repeat, x1 is given as mi, x2 is given as mi square, x3 is given as mi cube, x4 is given as ma, ln of ma, x5 is given as ln of tr by p. All these explanation what are the variables are there in the slide before. x6 is given by ln of b by p, x7 is given by ln of p by h, and x8 is given by ln of h, and obviously this is an error. So, actually when you do the transformations, then actually you get this multiple linear regression model. I am taking the model as given by the authors. I have tested that. So, that testing part, as I said, that is more on to DADM 1 course or basic statistics and probability course, or second course in the area of probability and statistics. That testing you can do and check the concept of hypothesis testing, normality test, non-normality test, and do that. Once I have that, I fit that model. What I need to do is find out beta hat, find out covariance of beta hat, find out S square, find out R square, find out R square adjusted. So, I have only done, because all these things can be, once you have the data set, please do that. That is for the extra knowledge, actually related to the assignment and the end sem. These calculations of R square adjusted R square, you can do it, but that will give you a lot of confidence. So, the values of beta hat, which is the vector, is this. Beta naught is 11.49, beta 1 is 0.47. I am only reading the first two decimals. Beta 2 is minus 0.01, beta 3 is 0.00 because it is very small. Beta 4 is plus 0.15, beta 5 is minus 0.85, beta 6 is plus 0.80, beta 7 is minus 0.40, beta 8 is plus 0.04. Based on that, you fit and find out the model. Now, we would now go a little bit in a different direction. In regression models, y finding and y it is good, but that is not the end of the day. In many of the models for ANOVA calculation, other different concepts, you need to find out a function of the values of beta, and that comes out to be very interesting. Consider this fact that rather than finding out beta, I am more interested to find out theta, which is a function of L, this T is transposed into beta. So, L is a row vector and beta is a column vector. When you multiply, theta is basically a scalar. So, if beta is k cross 1, then L will be 1 cross k. So, 1 cross k into k cross 1 gives you 1 cross 1, which is one element. Why we want to find out is very interesting. So, say for example, that I will use two different colors here, because that example will be coming up later. Consider beta as a vector is, and consider there is no beta hat. So, that is beta 1 is 0.2 and beta 2 is 0.5. So, if I have L as 1 comma 1, then the value of theta would be calculated as this. Theta would be 1 into 0.2. So, 1 is in red color, I will use the red color. The multiplication is would be, I will be use the black color, multiply. Then I will utilize this, I am already writing this, I will input the values, multiplied by 0.2, and the value for the second term is this 1 into 0.5, the total value comes out to be 0.7. Now, the interesting part is, if the first element of L is 0, then theta is beta 2, and if the second term for L is 0, then theta is equal to beta 1. So, depending on what is the scalar or the fixed terms of L, you can have different values of theta, which will give you a lot of information of actually beta. So, we want the prediction of theta, which comes out to be 11.6992 based on the last slide of the values of beta we found out. We can do by taking different sample size of n, and here it is what is important. If you remember, I had mentioned the actual estimate of beta hat in the long run is equal to beta, which is unbiasedness, and it has been proved. So, rather than proving it theoretically, I take, or we take, let us consider that that is a big data size of 20,640. So, we break it into different chunks, and considering the size of, say for example, about 5,000, we take such 25 blocks of 5,000. 5,000 I am just giving as a number, 25 also I am giving as a number, it can be anything. So, more number of chunks I take and I find on the beta values, that means beta naught till beta the last value which I have, and I keep repeating it and find on the averages. The average actually will turn out to be the actual population values of beta. Based on that, the theta value is calculated, which is L transpose into beta. That value comes out to be 11.6992. Larger the sample size in each sample, that means the blocks I am taking 5,000 which I mentioned, and the larger number of such samples I take, which I mentioned at 25, then in the asymptotic sense, in the real sense, the values which I just mentioned for the beta hats individually will slowly turn out to be the corresponding beta values for the population. Now, when we do and try to find out the theta values, we are all doing the problem based on the fact that ordinary least square is being used. Fantastic. In ordinary least square, what we do? We basically sum the errors, square them up and minimize that. Squaring the errors is exactly equal to trying to find out the variability, and minimizing that sum of the squares of the errors is exactly equal to trying to minimize the variability. But the question is that, if you remember, if it is a squared type of error, then for a plus error, the value is plus 2 into 2, consider the error is 2, plus 2 into plus 2 is 4, and for a minus error of minus 2 in minus 2 is also 4. That means, for an error which is positive and an error which is negative, both are being penalized to the same degree. So, with an error of 4, 4 into plus 4, 4 into 4 is 16, with an error of minus 4 into minus 4 is 16. So, that is point 1. That means, in some cases an error positive or error negative may have different consequences, which I will discuss. That is point 1. Point number 2 is that for very high deviations, say for example, for an error difference of about 50 square becomes 2500, which means the error term explodes. In that case, outliers would have some negative effect in trying to find out the answer. And this is basically the idea based on which we will now go into considering the concept of linear exponential loss function, which is Linux loss function, which gives us a good way of trying to handle both overestimation and underestimation by choosing the parameters actually. So, this I will read. It is seen that the penalties of overestimation with respect to underestimation are unequal, in the sense that the losses for overestimation when compared to that of underestimation are unequal. It may be unequal. To capture this asymmetric loss functions are used. One form of this asymmetric loss function is the linear exponential of the Linux loss function, and we will discuss that with examples in the next class with just the results. I will not go into much details. So, with this I will end this class. Thank you and very much and have a nice day.